welcome you all to this class on defects in materials. Okay. In the last class, we have discussed about how from a 2D lattice, a 3-dimensional lattice can be generated. What are the point group symmetries which are associated with that lattice? Okay. How to understand and read the International Table of Crystallography to construct a crystal structure. Okay. We mentioned a little bit about how a crystal structure can be constructed from the International Table of Crystallography, okay, especially looking at the special and general position coordinates and the site symmetries which are given in the table. Okay. So let us have a recap of that and go into a little bit in detail. Okay. What I am considering in today is one typical example which I had mentioned in the last class also, essentially a space group 4 having P4mm symmetry. So when we consider P4mm symmetry, it's essentially a tetragonal structure, okay, and the positions of the atoms, if we try to look at it, okay, it has got a 4-fold symmetry and a mirror symmetry associated, the 4mm symmetry at the lattice points and the center. And at the edges, if you look at the middle, we have 2mm symmetry. Then there are 3 types of mirror symmetry planes are also associated with it. Okay, right? The atomic positions are also given. Okay, these are all the positions we can fill the atom. Okay. So generally, if you look at any of the space group table, what they mention are the graphical representation when they show is only of the symmetry associated with the lattice, the graphical representation in the unit cell, where the symmetry appears, all the symmetries are shown. Another graphical representation is where only the position of a motive, asymmetric motive, if we keep it at any general point, how the equivalent positions are generated. Okay. And why only this is being shown, if we look at is the reason for this is because if we consider a general position, okay, when all the equivalent positions are generated, the complete symmetry operation has been performed only in this case. Okay. In other cases, if we consider where some symmetry elements are, that is, the motive itself has got some symmetry associated with it. If it is sitting at a particular point, that symmetry operation need not be carried out, only the other symmetry operations will be carried out. So the complete symmetry operation can be represented graphically only if we put an asymmetric motive at a general point. We will take up this with examples later in the class. Okay. Let us have some idea about these special positions. What are special positions? These are all the positions in the once the lattice has been created, okay, at different points. If we try to consider it, different type of symmetries can exist. Some points there need not be any symmetry associated with it, and some point in the lattice, if we consider, there could be some symmetries which are associated with it. The symmetries which are associated with these points, okay, are called as the site symmetry. Okay. The term wise site symmetry is used at that particular point, what all symmetry elements which are crossing through that point. It is something equivalent to a point group symmetry. But if we look with respect to that point, okay, where the site symmetry is there, if we consider the nearest neighbors which are going to be there, they will exhibit, that cluster will exhibit the symmetry which will be that of the site symmetry. Okay. And another factor also which we have to understand, that all the site symmetries which are being mentioned are subgroup of the maximum symmetry which the crystal exhibits. Okay. No, generally another thing which you do that to construct a crystal structure, what do? We keep a motif either at, an atom at a general point or a special position. Okay, we will consider this in the case of a P4 symmetry. Okay, space group. In this, if we take an atom, okay, we assume the atom to be a spherical, so it has got an infinite symmetry is associated with it. Okay, since it has got an infinite symmetry, okay, if we keep it at any specific point, okay, it will exhibit the symmetry of that point. At whatever be the lattice point, we keep that atom.
Special position or
special position, if we keep it, it will be all the symmetries of the special positions will also be coinciding with that of the atom. Okay. So essentially we can keep it anywhere, but where we keep it, at that point the lattice will have some symmetry. So it always matches with that symmetry. It assumes that symmetry of that lattice point. Correct? Though it has a full symmetry, it has an infinite symmetry. Okay. Suppose we keep it at the lattice point. The lattice point has got a 4 symmetry. So we require now all the symmetry operations can be performed on the same atom itself, since it is present on the lattice point. Okay. And as per the definition of point group symmetry, that point remains unmoved. So if you have an infinite symmetry, only one atom point is required. Okay. One atom has to be placed at that particular position. Okay. Suppose, for example, if we are keeping an atom at a point which is far away from it, that for example, if we keep the atom at this particular specific position, it is at a general point. Now by symmetry operation, for the same atom, now this atom has got only a one-fold symmetry where we have kept it. So though it is spherical, okay, and now it has to be by the symmetry operation of the lattice, we have to generate all other equivalent position. Okay. It is equivalent to when if we move all these atoms from here gradually, okay, maintaining that symmetry, then at the lattice point all of them will merge together and join into one. So only one, because of that we have to keep only one atom at that particular point, right?
That means if we put atom or motif at any general position, then we need more atoms.
Yeah. General position we require more atoms because equivalent position by symmetry has to be generated. If when we put it at a lattice point, depending upon the symmetry that dictates how many atoms have to be placed there. Correct? So that is what essentially is being done. At this point the maximum symmetry of the lattice it exhibits. So we have to put only one, okay, or the another equivalent point which exhibits 4 symmetry is this particular point. Okay. Similarly, if we put at these positions also, since it has an infinite symmetry, one is good enough, but now we know that another equivalent position has to be generated so that the symmetry of the lattice will be exhibited by the unit cell. Okay. So when we put an atom at a particular position, it should satisfy the site symmetry. But when it has been, when we consider the unit cell as a whole should satisfy the symmetry of the lattice. That is both these conditions have to be met. Okay. So like as I mentioned earlier, for if it is a mirror symmetry, there are 3 options are there. Okay. These are all the 3 possibilities. Okay. Which position the atom will occupy, okay, will be determined by what are the positions at which, if there is another atom which is being present, okay, then that consideration will tell, okay, suppose it is a compound which contains 2 elements, then the bonding between the atoms also will decide if one atom has occupied one position, where exactly the another atom will come. Okay. So if you look at this structure generally, if it is only one type of an atom which is there, what is the most likely choice is the one which has got the maximum symmetry, because that will have the lowest energy. Okay. Suppose the motif has got a different type of it is not an atom, we are putting a cluster of a molecule at that point, then what will happen? Then if the molecule has got the full symmetry, if a 4 mm symmetry it exhibits in this particular case, then we can put at this position one molecule each, okay, so that it satisfies the symmetry of the lattice. Or the other alternate position is at the center of the unit cell. If we are putting a molecule, okay, at this position which has got 2 mm symmetry, then the molecule, if only one molecule has to be kept there, then the molecule should satisfy have the 2 mm symmetry, okay. Then only in that case the molecule will occupy this position, because energetically also, if when we have to consider both of them, this is the most likely position where the molecule will occupy. So if you put it at a mirror symmetry position, then this should have the mirror symmetry should be exhibited by it. It can have a symmetry higher than that of this. It can be minimum symmetry which you should have is that of that side. And when we place it there, those symmetry elements also has to match with each other, okay. That is very important. I will come to that later. Okay. Here what we have done it is that in this particular case, if you put it at a general position, okay, it has a symmetry which is one-fold, so you can put an asymmetric motif itself there to generate the crystal having 4 mm symmetry, correct? Yeah. Now let us take the case, okay. The options which are available we have is that if you are putting an atom or an asymmetric motif, it can be 1A, 1B, 2C. These are all the various positions in which, okay, an atom or a motif could be placed, okay. So if you to exhibit the full symmetry, if we keep this motif at any particular point, okay, to maintain that full symmetry of the lattice, okay, or to satisfy the full symmetry of the lattice, it has to be kept at some specific positions, equivalent positions. This is what it is the general position, okay, which you see it in the internal crystallography, the graphical representation also it is being shown. What is the other position in which this could be kept, satisfying the full symmetry, okay, because here if you look at it, the mirror planes are both along the axis, correct. There is another mirror plane which is there, which is along the diagonal. So that position also could be chosen. So these are all the two positions in which the molecule can arrange itself around that specific lattice point, correct. Now if we rotate it by some arbitrary angle, then in this position it will have a 4-fold symmetry, but it does not exhibit the mirror symmetry. So this position is not possible, correct. So by an arbitrary angle rotation cannot be done, and so most of the time when we put a motif at a lattice point, the motif tries to arrange itself in such a way that symmetry elements of the motif and the symmetry elements around that lattice point are lying on top of each other, okay. Now let us consider a case where the motif is not an asymmetric motif, okay. It has got a mirror symmetry associated with it, okay. The other option which we have is that it can be, the motif can be kept coinciding with the mirror symmetry which is existing on the diagonal element, okay. Then in that case also, that is essentially rotating it by an angle of 45 degree, correct. Then if it is an asymmetric motif, we require 8, okay, that is the way it is. Suppose this motif itself is, the symmetry axis does not match. If I rotate it by an arbitrary angle from this position, then we have to, then 8 motifs have to be kept, okay. Or if we keep one motif at an position which has 1-fold symmetry, then another 8 equivalent positions will be generated where the same motif has to be kept, okay, so that the full symmetry of the lattice is satisfied. Only this way we can generate a crystal though the crystal motif or the atom has got a twofold symmetry or the molecule has got a twofold symmetry, if it is kept at an arbitrary position in this particular lattice, okay, at 8 more equivalent position it has to be kept, okay, so that the crystal exhibits the full symmetry of the lattice.
For this mirror symmetry motif, we need 4 equivalent positions.
No, for mirror symmetry, if the mirror symmetry coincides with that of the crystal. Suppose I assume that I am keeping this motif, this is at 45 degrees, at some angle 10 degrees from the mirror symmetry. Then I will have to keep around another 7 equivalent positions more, where the same, though the mirror motif has got a twofold symmetry, the symmetry of axis of the motif and that of the lattice, if you see the point where we consider they do not match, the symmetry which the motif in the lattice is going to exhibit is as if it has only one fold symmetry. So 8 more positions it has to be kept.
So that 8G or 8G means
8G means that G is the Wyckoff symbol, 8 means that how many equivalent positions which are required. Okay. And here it will become that in this particular case the number will be, since this has a symmetry which is 2, it will be only 4 motifs will be required. Okay. Suppose we keep this same motif, okay, around mirror symmetry positions, what all positions which we have to keep it. Like as I mentioned earlier, the motif will be kept with the mirror symmetry coinciding. We can keep that, one of the option is keeping it with mirror symmetry along the diagonal, okay, or it can be along the axis A and B axis, or at the center, okay. Also there is a mirror symmetry plane is there which is parallel to the axis. So in these 3 options, these are all the 3 ways in which it can be arranged, okay. Here I am considering another case in which the motif has got the full symmetry of the lattice, okay. That is another case where the symmetry which the motif is exhibiting is only a mirror symmetry, okay. Because if we look at this particular position, the symmetry of this position is 2 mm. This motif has also got a 2 mm symmetry. So only one motif has to be kept at this specific position. If I keep a motif with a mirror symmetry, this motif, if I try to keep it there, there should be another equivalent position, the same motif should be kept. So it is equivalent to generating a cluster like this, which exhibits, this cluster exhibits the 2 mm symmetry. Now this can be kept at this lattice, particular lattice point, okay. So this generates the full symmetry of the crystal, right. So if I put this asymmetric motif at any particular position or at 2 mm position, now what we can make out is that this structure does not exhibit the symmetry. This has got only a 4-fold symmetry, all the mirror symmetry has been lost, correct. So this is what it will happen. So if only 4-fold symmetry is there, then the space group of the crystal is P4, okay. It is different from what the space group symmetry which we are considering now, right. If we take a crystal with a if we take a motif with a 4 mm symmetry, okay, and if we are trying to keep it at a point which has got the 4 mm symmetry, then we have to keep only one motif. So here the motif which is used is a square, okay. That is a molecule which has got only 4 mm symmetry, okay. Then we have to keep only one molecule either at the lattice point or at the center of the lattice, okay. So here what I have shown is that an asymmetric motif, okay, summing it up all together, okay. If we take an asymmetric motif, okay, and if we wanted to put it, okay, place it at different special or general points in the lattice, okay, what sort of a cluster we should be placed so that that will satisfy the full symmetry of the crystal which we wanted to generate. Okay. So, this is the way it will happen in this case. Okay. This is what is going to be the cluster which has a 4 mm symmetry. If I wanted to keep it around another position, it is the same cluster which can be kept at the center of the unit cell. If it is around the special point which has got 2 mm symmetry, then this is the way it has to be kept. Okay, satisfies the 2 mm symmetry, and in this case it has to be, this is the way a cluster will have to be kept, so that it satisfies that symmetry element when the mirror symmetry is along the diagonal, okay, face diagonal, and this is the particular way in which it has to be kept, okay, when this is along the one of the axis, okay, and this is the sort of a cluster which has to be kept around this mirror symmetry axis. Okay. What we have done, we have taken only a motif with one fold symmetry which is placed. Okay. If you look at it here and this one, it looks like almost the same type of a cluster, but only thing is that what we have considered is with respect to width axis, correct? Another important aspect which we have to consider when we wanted to construct a crystal structure is that the special positions and general positions are given in that International Union of Crystallography, a table which gives the coordinates of the Wyckoff positions are given. Okay. Each of the special positions, only one type of an atom can be kept at each position. Suppose we try to keep at any particular point, okay, one type of an atom. For example, if we consider the 1A position, if we keep one atom, and the same type of an atom if we keep it at the B position also, it is just not possible, because if we keep the same type of an atom, now this structure will exhibit a symmetry which is not P 4 mm, it becomes I 4 mm, right. So, it becomes a body centered tetragonal. So, the symmetry changes. Okay. So, each of these points, each of the special positions or the general position, a specific type of atom only can be kept, correct? The another information is that now we know that at each of the position the same type of an atom cannot be kept. Suppose we assume the case where we are keeping a different type of an atom, that is, consider a material which contains two elements A and B. Okay. Then the question comes is that we can have with AB having different composition. So, if you have a different composition, the stoichiometry will be different. So, we can we create a crystal with any stoichiometry? That is, can we create a crystal having P 4 mm symmetry with any stoichiometry or not? That is the question which has to be answered. Or is there any restriction on the stoichiometry which we can have for a specific type of space group symmetry under consideration? This, if we look at it, okay. For example, suppose we take an alloy with a composition AB3, okay. If you assume that the A atom can occupy either 1A or 1B position, what all positions which the B atom can occupy? Either 2C position, or with the Wyckoff position 4D, 4E or 4F or 8. So, if we take the ratio between because the number represents the number of atoms or the molecule which will be there in the unit cell. From this we can determine the stoichiometry. From this, if we look at it, if A atom occupies 1A and B atom occupies 2C, then it will be AB2. if it is between A or B and between D position E or F, it will be AB4, okay, or between 1 and general position, it has to be AB8, okay. So, or suppose we have 3 elements which are present. A atom occupies 1A or 1B, B atom occupies 2C position, and C atom occupies any one of these 4D, E or F position. Then it can have AB to C4, this is the stoichiometry. So, these are all the stoichiometry which the material can have. Okay. In addition to this stoichiometry, what we have to consider in this specific case is that when we wanted to construct a crystal, okay, the number of atoms which are going to be there in the unit cell is also important. That information is also available in this Wyckoff position table which is given in the International Union of Crystallography. That can be used to find out what positions with the same stoichiometry but with different molecular formula. When we talk of the molecular formula, we talk about not just the stoichiometry between the elements, what is the total number of elements which are being present. That means that an AB2 structure, when we consider the stoichiometry, it could be 2 atoms of A and 4 atoms of B. That also have the same stoichiometry, correct? Because of that, so we are considering a case where there are 2 types of, that is one molecule or one crystal where the stoichiometry of the alloy and the number of elements which are going to be there is only just that in this particular case AB2. If you consider only 3 atoms are going to be there in that unit cell. There is another case which we can consider where with the same stoichiometry but the number of atoms which are going to be there is 12. Okay. If that is the case, then we can make out that in this case when it is going to be total 3 atoms, the only possibility which the atoms can occupy, possibility where the positions in the unit cell the atom can occupy is that B can occupy 2C position, because that is at C position 2 atoms will be there in the unit cell. Another is A atom can occupy either A or B position, Wyckoff position, correct? And suppose the, as I mentioned, the molecular formula is A4B8, then what can happen? In this particular case, essentially the position which I has to occupy is that A has to be 4 atoms. So, one of these 3 positions only it can occupy, option, and the B has got 8 atoms. So, that has to occupy only these positions.
That's why A3B6 is not possible.
That is why A3B6 is not possible, correct? Now, I had just shown in this transparency, okay, these possibilities which we have discussed, okay. Here if we consider, okay, we have an A atom which is occupying the corner and the B atom is occupying the C position, that is this is 1A position. In this particular case, A atom is occupying the B position and C position is occupied by the B atom. So, these are all the 2 configurations, because sometime back in the previous slide I showed it just with respect to coordinate positions. Now, it is a graphical representation of it. Now, we can make out that these are all the 2 options which are available. So, which type of an option which is going to exercise will be determined by what is going to be the energetics. In this specific case, if we try to look at it, both these options are going to be the same, because if I move the coordinate from here to this position, okay, now I will be essentially generating this particular one, okay, there is no difference. Here what I am considering, it is not A4 B8, it is A2 B4, okay. So, if this is the molecular formula A2, B4, then A atom will have 2 equivalent positions, B atom will have 4 positions. Okay. In that case, the A atom can occupy only the 2C position, correct? The B atom can occupy 4 choices are there for it to occupy these positions, correct? Which of the one which it will be actually in the particular crystal, which option will be exercised, okay, or which type of a crystal structure will generate will be determined by the energetics. Okay. We have to look at the energetics of the all the 3 configurations for the particular atoms under consideration, and which lowers the total energy of the unit cell. That is the configuration which it will choose.
It is not possible to occur A position and B position simultaneously for AB2 structure.
A position and B position.
This AB2, na?
Yeah.
And first we put A.
No, the first one has got in the unit cell one A atom, that is the molecular formula, only 3 atoms in the unit cell. That is one consideration. Another is you consider another set of a type of an atom, 2 types of an atom, where in the unit cell the number of atoms in the unit cell is 6. Then what are positions which are possible in these 2 cases? Okay.
No, like that A2B4, na?
Yeah.
A2B4 means A should be 2 atoms in the unit cell.
Yeah.
Okay. So for 2 means for this A has to be
See,
put in 2C position. We can't put in A position and B position.
because as I mentioned, if we, the first rule which we have to follow in this is that only one type of an atom can be put at one position. If you put it in another position, then the symmetry of the lattice has changed. Now the space group symmetry is not the same. That is not possible. That is why this is the only option which is available. Okay. The next class what we will discuss is how to construct a crystal with some examples. Okay. We will take it up. We have just mentioned that using a crystallography how we can do it. Okay. It is essentially different types of crystals are which we know. Okay. How using this table, how various types of crystals could be generated. Okay. We will stop here now.